Yeah, thank you. So thanks to the organizers for the invitation. It's always a pleasure to be in Lumini. So I want to speak about part of my Long John project with Laurent Farc about a notion of local acyclicity in p-adic geometry. And I want to mention the motivation in a second, but maybe it's best to first recall the definition in the world of schemes. So let's first recall local acyclicity. For schemes. This was defined somewhere in SGA, I think. So let's put ourselves in the following situation that you say have f from x to s, a finitely presented map of schemes. And let's say that A is a complex of, well, let me actually, throughout the whole talk, take as my coefficients FL, and L will always be invertible on whatever space I'm working on. Everything will generalize to more general rings, but some isolated statements are slightly easier to state if it's FL, so let's stick to this. Let this be a complex of constructible sheaves. Bounded. And then there's a definition that A is F locally acyclic. Also just abbreviated to FLA. If the following condition is satisfied. So for all geometric points x bar of x mapping to a geometric point s bar on the base S, and a generalization t bar of s bar. So you have this diagram that x bar maps down to s bar, and then this is a specialization of the point t bar. The following happens. So on the one hand, you can look at the strict localization of x and take the global sections of A there, which, by the way, because this is a strictly local ring, it's just a stalk of A at this point. And on the other hand, you can take the fiber product to the strict localization at T, and you ask that this is an isomorphism. And so in particular, this means that the restriction of A to a special fiber is basically determined, or it's at least very strongly correlated by the restriction of A to the complement. Because if you want to know what it looks like on a special fiber, so at a geometric point x bar there, then you can compute this in terms of the right-hand side. But for the right-hand side, you can take a generalization which lies outside of your special fiber somewhere on the base. And so that information is purely somewhere on the generic fiber. And so this is local acyclicity, and then there's a small strengthening of this notion that A is F universally locally acyclic. F ULA, if true after any base change on S.
This generalization T is exist or
Et al. Okay. So let me give some crucial properties of these of this notion. And then let me say why we care about this notion. So being ULA is FPQC local on S and smooth local on X. If F is the identity from S to S, then A is, well, it's ULA. If and only if A is Lease. Another important case, which is some incarnation of smooth base change results, is that if F is smooth and A is Lease, then A is F ULA. And then another important property is that proper push forwards of ULA sheaves are ULA. So this is in the situation where you have two things over S and H is proper. And so if you have a ULA sheaf here on Y and then you take its proper push forwards, then it's ULA on X. And another important property is that exterior tensor products of ULA are ULA. So here you have x1 and x2. And then you can also have the fiber product. And if you have ULA sheaves A1 on x1 and A2 on x2, then the exterior tensor product on x1 times x2 is again ULA. Okay, so one important application of the theory is in geometric Satake. And so this application is our motivation for studying this in p-adic geometry. So this is to the so-called fusion product of perverse sheaves on the affine Grassmannian. So what's the setup there? So let's say X is some curve, usual curve, Yeah, smooth projective. Let's not get ourselves confused here. Over some algebraically closed field. And let's also, let's say, fix some reductive group over K. Then there is this relative Grassmannian x over x. What does it parameterize? It parameterizes G torsors E over x plus a trivialization outside of a given point plus a trivialization. Parameterize such a point in x which gives you the projection and a trivialization of the thing outside the point. And so all the fibers of this are actually isomorphic to FN Grassmannians. So the quotient of the loop group was a positive loop group. Because if you fix your point, then by Laszlo, giving such a G-torsor with such a trivialization is equivalent to just giving it on the formal completion with such a trivialization. And that's, if you fix a coordinate at x, is precisely what this quotient here amounts to. And this, there's also a two-variable version. Where, well, how does this parameterize? E and 1, 2 points, and E restricted to x minus the 2 points. It's trivialized. And so this is actually some kind of funny object, because if you take this and restrict it to the complement of the diagonal, then you somehow have the trivial G-torsor away from those 2 points, and at those 2 points you can choose arbitrary modifications, both of which are given by one FN Grassmannian. And so there it's actually isomorphic to just a product of 2 times this thing. Again, of course restricted to the complement of the diagonal. But when you restrict this thing to the diagonal itself, then, well, x1 is x2, so you're just trivializing this away from 1 point. And so it's actually exactly the same thing as just one copy. So this is a slightly funny degeneration of 2 copies of the same object to 1 copy of it. It looks slightly less strange if you remember slightly more about this modification. So there's also a version called Clotilde. So this parameterizes slightly more data. E 2 points, but actually, so E1 and E2. And E1 restricted to x minus x1, so it's more to E2. So in some sense, you record an intermediate modification with it. So then there is a projection from the sky where you forget the intermediate modification. This is improper. And an isomorphism of wave. over this thing. And one can think of this as some kind of twisted exterior product of two copies of the Grassmannian. In the sense that, well, locally you're always parameterizing two modifications of G-torses. So for a suitable definition of what this means, you got that. Okay, so in geometric Satake, you're interested in the perverse sheaves on this F1 Grassmannian. And so if you have A and B, which are in the Satake category for G, which are the L plus G equivariant perverse sheaves on this Grassmannian, then you are able to globalize both of them to perverse sheaves on this global F1 Grassmannian Guru X, the globalizations. Which fiber-wise are just your good old A and B. So. And now you're trying to produce a new sheaf on your F1 Grassmannian, which is a convolution. But then there is this other way to do it as a fusion. And so how does fusion work? You can take the exterior product and restrict it away from the diagonal. So that's now a sheaf on, well, two copies of this restricted to the diagonal, which is the same thing as this two-parameter guy, restricted away from the diagonal. And then there's the following theorem. I guess it appears in the work of Rencontres and Vilonen. That this thing there admits a unique extension to a sheaf called the fusion of A and B. On this two-parameter Grassmannian with the condition that is universally locally acyclic for this map. And so this is an incarnation of the statement that I said there, that if you restrict such a ULA sheaf to a special fiber, so what this is on the diagonal is essentially already determined by what it is away from the diagonal. And then you define this to be this global fusion restricted to this diagonal, or even restricted to a point on the diagonal. Where it now is is again a sheaf on the F1-Grassmannian, which is called diffusion. And one critical property of this procedure is that it obviously is symmetric in A and B, because there's everywhere symmetry which switches the two factors. So, and so this shows that this monoidal structure that you put on the Satake category is a symmetric monoidal structure, essentially, which is a critical ingredient to the proof of geometric Satake. And it's actually easy to see that there is at least one such extension. So, remark. Easy to produce one extension. Because you can take some kind of twisted exterior product, twisted in the same sense that it was twisted there. So you can define this on this convolution version of this global F1-Grassmannian, which is ULA, which by preservation of ULA under exterior tensor products, this is ULA for this projection. And on the other hand, being ULA was preserved under proper push forwards, and so this implies that also R pi lowest of this thing is ULA for this thing. And so this implies that this thing here is actually canonically the fusion. But the way this existence was proved used an ordering of the 2 points. This Grotthilde thing is not symmetric in x1 and x2 because there's an order in which you make some modifications. And so a priori this thing wouldn't be symmetric in A and B, but this is. And so this formula for what fusion is also tells you, if you look at what happens over the diagonal and use proper base change, it tells you that it actually is the convolution. Okay. Okay, so that's what we would like to mimic in p-adic geometry, and so more precisely, when x is some of the Falk-Fontaine curve, we would like to do the same thing. And so we need an analog of this theorem that tells us that there is a unique way to get this extension. And this should be pinned down by what this ULA condition is. So now let's switch to p-adic geometry. So now let's say, so I should say that everything works for diamonds. But the story I want to tell is already interesting just for adic spaces or for rigid spaces. So and so for exploratory reasons, let me stick to this more familiar setup of rigid spaces. let's say f from x to s is a map of rigid spaces that I consider as adic spaces, also over some non-Euclidean field K. And it's evident that I would like to view them as adic spaces because in the definition of local acyclicity for schemes, I was talking a lot about geometric points of my schemes. And rigid spaces don't really have enough geometric points, but adic spaces do. So it's certainly a better choice to work with adic spaces here. But there is an important problem that one immediately runs into is that there are no specializations into Zariski closed subsets. So, like a point away from the diagonal specializing into the diagonal. And the possibility of specializing like this is of course critical to the argument that you get this unique extension. Because if all your condition is doing is comparing fibers inside delta and outside of delta with another, then you won't get any such information. So what's the example here? So let us recall how the points of the closed unit disk look like. Let's say S is a ball over K. Then topologically, what does S look like? Well, it has all these classical points, which form some kind of totally disconnected set. And then somewhere you have a Gauss point. And then there's all this tree-like structure that emerges, corresponding to all the different Gauss points on different disks. And then the only specializations that actually exist in adic spaces, there are specializations from the Gauss point to very close by points, some higher ranked points. So, but you will never be able to specialize from somewhere here directly to classical points. So on the Zariski closed subsets, they would just be points at the boundary of this tree here. But all the specializations just happen at these branches of this tree very locally. But let's still analyze what the direct analog of the condition for schemes would be now for adic spaces. So star, which is that for all geometric points. So okay, so A is a complex. On X. So this maps to a geometric point S bar of S, and then I can have a generalization T bar to S bar. I can ask that the global sections on the strict localization, which again are just the stalk of X at this point, that they map isomorphically to this thing. Then there's the following observation. So something nice, but that's rather a disadvantage for us now, is that the strict localizations, like X localized at X bar here, that they are an extremely simple form for adic spaces, for analytic adic spaces, like rigid spaces. So the strict localization XX bar is actually just of the form sparse C++, where C is some complete algebraically closed field, which is some of the residue field at X. And C plus is a certain open and bounded valuation subring. So the points of the adic space are given by certain valuations, and this gives you these valuation subrings. And so in particular, topologically, it turns out that this is the same thing as the spectrum of C++, which is a finite totally ordered set of points. Totally ordered under specialization. And any open subset is again of the form for maybe a different open and bounded variation subring C plus prime. Sorry, what pi? Where? Yes. All right, I mean, I could also just mod out by topologically important elements. So then this thing is a variation ring. And, sorry.
Is C necessarily automatically also a bounded characteristic as opposed to
Yeah, the question is how you define the strict localization. I mean, certainly the Tal topos is isomorphic to the Tal topos there. Let's just say that. I mean, somehow if I implicitly always complete my things, then I mean, if you complete a separable closed thing, then it's automatically algebraically closed. So if you agree that forming this localization here implicitly involves a uniform completion, then it really is of this form. But this means that this funny fiber product here, which for schemes could be some very complicated scheme, for adic spaces it's actually extremely simple. It's just a localization of X at some other point. So this is actually just a stalk of A at Y bar, where Y bar is the minimal generalization of X bar mapping to T bar. And so so this turns out to actually be not such a very interesting condition. And so more precisely, you can show that a star holds universally. I mean, after any base change in S. If and only if A is what's called overconvergent. I.e., for all specializations, y bar to x bar, there is a natural map from the stalk of A at x to the stalk of A at y, and this is supposed to be an isomorphism. So it actually doesn't even depend on the morphism. Let me just remark that this notion of overconvergent sheaves is something that comes up rather frequently in rigid geometry, and actually overconvergent sheaves are exactly the sheaves on the Berkovich side. So so in the Berkovich setting, you collapse all these points here to one point by passing to the maximal Hausdorff quotient, and this somehow forces it that there can't be different information at those points, so all these things must be isomorphisms, and you can prove that this is precisely the condition that you become a sheaf on the Berkovich space. But in particular, this notion, will never tell you anything about these different fibers that we would like to compare. And so obviously we need to put some further conditions, and so we need to put some finiteness type assumptions. And so for this, let me give a reminder on constructible sheaves. Which is a notion that at first is a bit counterintuitive in rigid geometry. So, and to motivate it, let me recall that if S, or let's call it T, is any QCQS, so it's any spectral space, spectral topological space, then a sheaf F of FL vector spaces is constructible if there exist, and let me stress this, quasi-compact open empty set is U0 contained in U1 and so on. N, which is all of T. Such that F restricted to any such locally closed stratum is Lease, so locally constant, given with infinite FL vector space. And so this can be easily adapted, so definition adapts easily to the état site of QCQS schemes or adic spaces. But for schemes, I mean, most of the time you work with Noetherian schemes, in which case all open subsets are quasi-compact. And so one tends to forget about this quasi-compacity there. For adic spaces, this is not at all true. So let me give an example and a non-example of a constructible sheaf. So an example would be the extension by 0 of FL, where J is, say, the inclusion of the ball, the closed ball into P1. And the non-example, which we would maybe much rather like to be a constructible sheaf, would be a skyscraper sheaf, I lower star of FL, where I is just the inclusion of the origin, say, into P1. Just a point into P1, just 0. The issue with this example is that the stratification would like to put is some of the stratification into this closed subset and its open complement, but the open complement is not quasi-compact. It's this increasing union of larger and larger balls. But, so this seems like a problem that constructibility is such a weird notion, in particular that things concentrated in Zariski closed subsets will never be constructible. But now we will turn this around and make it an advantage. Okay, so more precisely, let me first state 2 results about constructible sheaves. So one is that if you have such a complex, then this is, if it is constructible and also satisfies this condition that it's overconvergent, so it comes from the Berkovich setting. Then this happens if and only if it's actually Lease. So there the point is that for such quasi-compact stratifications, you will always be able to find specializations connecting two different strata. So for example, here, there is this specialization from the Gauss point to one rank 2 point, which lies in the complement. And so you can't actually have such a sheaf, because this would not be overconvergent. And another proposition is that if A is constructible, then it is Lease in the neighborhood of any rigid point, neighborhood of any classical point. So any classical point is somehow either firmly in the ball or firmly outside the ball. And so there it's Lease. And so you only see this non-Leaseness on these non-classical points. But this means that these constructible sheaves precisely have the property that anything that's happening on a Zariski closed subset also happens in a neighborhood. And this is, of course, exactly the behavior we want to connect what's happening on the diagonal with what's happening outside the diagonal. And so Next page. Right, so now I can finally give the definition. And let me just define universal local acyclicity. If, first of all, we want this condition, the analog of the condition we had for schemes, which by that proposition over there just means that A is over-convergent. And now this is the universal part, after any base change in S. For all étale maps U to X, where I want the composite F restricted to U to be QCKS. If you take the relative compact support cohomology of A, this should be constructible. And so the analog of this condition is always satisfied for schemes by general properties about preservation of constructible sheaves under lower Schwick. But it's absolutely not always satisfied. I mean, I didn't put any constructibility on A to start with, so you obviously can't expect this in general. All right. And so, with this definition, you can have all these basic results. So, being ULA is smooth local on X. And I mean, I could even write V local on the target. Yes. And what was the other things? If F is the identity, then A is FULA. If and only if A is Lease. This is actually an incarnation of this proposition up there that if it's over-convergent and constructible, then it's Lease. So if you just apply the second part of the definition to U being X itself, then you see that, well then, Schwick along the identity is just this thing itself, so you ask that A is constructible. And so this reduces to the proposition up there. And then if F is smooth and A is Lease, then A is FULA. And then the case of push forwards, and exterior tensor products. And we also have a version of the theorem of Merkovich and Vilonen. So that actually needs slightly harder hypotheses. So the uniqueness statement is slightly weaker, but it's still good enough to prove the symmetry of the convolution product. Okay, so, but in the last, how many minutes? 5? 6? Okay. Let me make a connection to Laurent's talk and talk about an application to this business of formal and cohomological smoothness. So. So and I mean that applications are really only interesting when we work with diamonds, etc. So let's say we have a map of small V stacks. That's representable in locally spatial diamonds, plus some small finiteness conditions. So compactifiable and some dimension of f is less finite. Then if you have any FUA complex, then the following things happen. Then, okay, so let me denote by, let me define a relative Verdier dual as the R Hom into of upper Schrieg. One is that the formation of this relative dual of A commutes with any base change in S. And secondly, you're able to say something about this upper Schrieg functor. So in general, the upper Schrieg functor is the one that's hard to calculate. But in the presence of a ULA sheaf, you can at least compute a certain twisted version of it easily. So namely, you can compute the R Hom of A into R of upper Schrieg. Just in terms of F upper star twisted with the relative dual of A. And so in particular, if A is lambda, then this reads well, the dual is just R of upper shriek. And so the theorem is that if F with the previous hypothesis is formally smooth, and again plus some finiteness assumptions, then the constant chief is ULA. And actually also the dual of lambda, sorry, FL. And so the second, this means that you, on the one hand, you have this formula that just said that you can compute the upper shriek functor in terms of F upper star. But there's actually a dual to the statement that's also true in the setup, is that you can compute the F upper star in terms of the F upper shriek if you put the R of upper shriek here, dualizing on the other side. And so this actually means that many of the arguments that you can do for cohomologically smooth things, they also work under the slightly weaker assumption that FL and the dualizing are universally locally acyclic. Oh. Yeah, let me stop here.